case approaches to least squares regression. And Michal will give the talk.
Thank you. Hi, this is joint work with Ken Clarkson, Michael Mahoney, and Manfred Warmuth. Okay, so just to, again, we're just reviewing the same sort of experimental design problem from the previous talk, right? We have n experiments parameterized by d-dimensional vectors, and each experiment has a hidden response, which is linear plus Gaussian noise. And we want to pick a small subset of experiments to look up those responses and best estimate the linear model, the W star. Right, so that's the classical experimental design problem. Now, so again, we have to sort of decide what optimal here means, what best means. So as seen earlier, one way to do this is via a-optimal design. So we can sort of motivate this by saying that we want to find the unbiased estimator that minimizes the mean squared error. So as seen here, right? So it's a sort of minimization of this mean squared error conditioned on that unbiasedness constraint. If we had all responses, then we know that it's classical result that the minimizer, the best unbiased estimator in that sense, is actually the least squares estimator, and we can actually compute the mean squared error given all our assumptions, and it's going to be sigma squared, which is the variance of the noise, times the trace of this sort of inverse covariance matrix, right? This is we will call this phi. This is sort of like an important quantity describing the sort of a problem-dependent quantity describing the experiment setup. And so we can sort of ask how good can we pick a subset? What sort of bound can we get for a small subset of some size in terms of mean squared error? So we can adapt this from a result by Avron and Moutsidis to show that for any epsilon, there is an experimental design, so a subset S of size k at most d plus phi over epsilon, such that the mean squared error is below epsilon times the total noise in the problem, which, since we have all of these assumptions on the responses and on the noise, this is just n sigma squared, right? So our goal here is sort of to extend this framework beyond, so that we don't have to require these strict assumptions on the response model and the noise. So can we sort of extend the model but recover similar bounds? So how can we extend the model? So one natural way to do this is as follows. So let's now say that our response vector y is just some random vector. Just assume it's finite second moment. And so now we have to sort of define what the optimal linear predictor is. We can define it as the minimizer in expectation of the squared error. And now the noise just follows as the deviation from the best linear predictor. So now, just to make sure that this is consistent with what I just was talking about, right? If we pick a y in such a, if y is such that by the definition the expectation of the noise is 0, then we are in the statistical regression case, as seen moments ago, and sort of those two notions match completely. However, what's sort of interesting here is that we can also capture the model where y is simply a deterministic vector, right? And so the noise has no variance, but it's biased. And so our model sort of is an umbrella over both of those two extreme settings. So the sort of the second setting is also has been sort of commonly studied in computer science and learning theory. So the interesting phenomenon here is that in the statistical setting, under sufficient number of assumptions, and as seen earlier, we can pick a fixed subset S, a fixed experimental design that will essentially work best. Whereas in the worst case, we are forced to randomize because of the adversarial nature of the noise. So for that purpose, we sort of extend the definition of the experimental design to the random setting, which just means that we allow the subset to be random and we allow the estimating function to be random as well. So here's the main result. So let me parse this. So basically, we're saying that there's always a random experimental design of size order d log n plus phi over epsilon. Phi, again, is this sort of problem-dependent quantity, trace of x transpose x inverse. And this design has the following properties. First of all, for any random y, for any random response vector, right, the experimental design is unbiased with respect to the defined least squares problem. And the next line is the bound on the mean squared error we obtain, which looks slightly different than the one I showed earlier. But this is sort of necessary. We have to sort of account for the worst case nature of the noise. But this bound essentially, in the special case, it recovers the one we've seen before. And the sort of the main trade-off here is as a log n factor that we suffer. But otherwise, this essentially matches what we've seen in the previous bound. So what's cool about this is that it's sort of a very broad result in that sense that it does capture the statistical regression settings that we look at classically, right, where the noise is mean zero. But in particular, we can have responses have the noise of the responses have different variances, or the responses might be correlated, and in which case the covariance matrix is arbitrary. And we also cover the sort of the computer science setting where the y is a fixed vector. So just a little bit about the sort of how we get this result. We combine sort of several techniques. So first, to sort of stay true to classical experimental design, we require that the estimators be unbiased. And that is achieved via the technique called volume sampling. And to obtain the error bounds that we need, we use IID importance sampling. So we use certain importance sampling distributions. One of them mentioned earlier, levered score sampling, has been used many times for linear regression. The other one, interestingly, comes up inverse score sampling. So this comes up in context of our results specifically because we're trying to minimize the mean squared error, and somehow levered score sampling is not the right distribution to minimize mean squared error. So a little bit about volume sampling. So this is a joint distribution over subsets of size d. D is the dimension again, right? So we're sampling a subset of n rows of matrix X. We're sampling d of them, and we want the subset to be the probability of the subset to be proportional to the squared volume spanned by the rows. And so this is a joint distribution, but it can be sampled from efficiently. And one of the properties that it has that we're most interested in is this connection to unbiased least squares estimators. So in fact, we will use a recent result in a paper by me, Manfred, and Daniel Su, which shows that volume sampling not only generates unbiased least squares estimators, but in fact, it can be used to correct the bias of any least squares estimator of any IID sampling, any IID importance sampling used to generate a least squares estimator. So specifically, we can, if we have an importance sampling distribution chosen however we want, importance sampling distribution Q, we sample a bunch of samples from that distribution. We can just introduce a small volume sample of size d to that, and the least squares estimators appropriately rescaled least squares estimator solved for the combined sample is exactly unbiased. So that's what we exploit, and putting the volume sampling together with the two importance sampling distributions mentioned earlier, we are able to obtain the error bound mentioned in the main result. So in conclusion, we sort of look at a framework for experimental design with arbitrary responses, and we show that the sort of worst case bounds we can obtain are actually very closely match the ones that can be obtained in the Gaussian setting, which is perhaps surprising. And of course, a number of open problems remain. For one, we believe you can actually remove the log n factor and still maintain obtain this unbiased estimator. And the other thing is that from our results arises a sort of a notion of a minimax optimality criterion for experimental design, where we essentially take maximum over all random response vectors and minimum over all random designs. And while we have bounds on this minimax value based on our main result, we don't know how to find the minimax optimum value or how to even approximate it. So that's very much open. Thank you.
Bad is it to be biased?
So the unbiasedness part, first of all, we use this for several reasons. One reason is that it's sort of not clear how to come up with a minimax optimality criterion because essentially if you look at this, the criterion you have here, we're sort of subtracting this mean squared error of the least squares estimator. And the reason that this makes sense here is the least squares estimator is the best unbiased estimator. Whereas if you were not unbiased, if you were considering minimax experimental design for any estimator, it's not clear what in this context would be the best to choose from. So that's one motivation. The other motivation is actually we use the unbiasedness in the proof of the main result. If we didn't have that, then it doesn't necessarily seem like such a general framework would, such a general result would be possible, or it will look the same way. And also in some context, you sort of, for the statistical analysis, you might want to have an unbiased estimator to understand better the confidence intervals in your problem.